Hello everyone and welcome to today's video. In this video we will talk about the modeling and UML diagrams. Uh, One of the basic usage of the UML diagrams is that it helps us to abstract the whole concept of the program that we want to write. So basically it helps us to define the models, the data models that we're going to store the information during processing them as an instance or as an object in the memory. So let's talk about this example, and I will also tell you why these models are important. Imagine that you have a class of animals, and this class of animals is an abstract level of all the animals or beings that living on the earth. In this class, many different subtypes are living. So for instance, dog is a subtype of animal, or human is a subtype of animal, or any other species is the subtype of animal. And they can have similar behaviors, like they can eat, they can sleep, they can speak. But eating between the dogs and humans can be different. So they are different. So this is what we can say both can do, but they can do it in different ways. Keep it in the mind. We will talk about this later. And this is what we call in the programming as a polymorphism. The polymorphism means that you have a similar method, but this method, depending on the dynamic type of the object, can return you a different result. So the result of this method, it depends on the dynamic type laying behind this method. So we call it the static type, and these are the dynamic type. So let's talk about why these models are important. Imagine that you have a piece of paper, and in this piece of paper you have a limited amount of space. So it's a start and it's the end, and there is a finite amount of space to work on. So whenever you want to do something, you need to put something here. If you want to do a task or daily job or whatever, you need to put it on the paper, piece of paper, and then you will use this paper, the information inside this particular part of paper, and then you can either use this information to create another piece of information, or you can store some basic information like the temperature, or I don't know, the humidity, and this data can be used in another process to do something else. So as you see, I'm referencing something here as I'm processing something here. And these piece of papers can be also equivalent to the piece of memories that we have on a computer. So on a computer you have a limited amount of space to work, and whenever you are instantiating an object like dog. We're storing this instance object in a piece of memory, and then this instance will exist as long as there is a reference to it. So as soon as the reference is gone, there is a mechanism in the, for instance, Java virtual machine, which called object collector, garbage collector, which will free this piece and make it available for another instance. So this model helps us to occupy a piece of memory in a very convenient way. So we can wrap some functionalities and some detailed piece of information about the dog or about the human in the memory and access them by just simply referencing this object stored in the memory. So let's go further and talk about our model that we are using for the project. In my project, I have a robot, and robot stores a certain piece of information. So in this case, a robot has motor here, and a robot, as you see, I have a cardinality. A robot can have either one at least or more than one motors. A robot can have a sensor, ultrasonic sensor, and it has just only one ultrasonic sensor. In this case, I want to have just one ultrasonic sensor. Or it can have also just one touch sensor. So in the robot, I'm storing other piece of informations that I'm gonna use. So I'm wrapping in a robot object. Imagine this is my piece of paper. I'm wrapping the relevant information about robot in one piece of memory. So whenever I want to use these information, I'm just simply accessing my robot object and I'm reading those information from the robot. Further on, we have a motor handler. And motor handler has a robot, so it has implicitly access to the motors, to the sensors, and also a handler has a sensors listener. So this is our listener class. So the listeners can have an abstract representation. This abstract representation can be extended as a touch listener or ultrasonic listener. So we have an interface. The interface can be implemented. This is the implementation symbol in the UML diagram. It can be implemented by an abstract representation of the interface, and this abstract representation can be extended. So we have the same pattern here also over events. So we have an abstract, we have an event interface, and this event interface can have an abstract implementation, and this abstract implementation can be extended as a motor or sensor. So we just learned two important uh, thing: implementation, implements, and extends. These two keywords are very common in programming languages. Basically, in Java, we implement the interface and we extend the classes. But in C Sharp, you just simply put the interfaces and classes back to back. So there is no need to distinguish using the keywords like implements or extends. As you see, we have another uh, symbol here, which tells us this class has a property, and the property is a sensor listener. The sensor listener is a property of an event, as the robot has three different properties, which I talked at the beginning. And also, we are having a control, and a sensor listener has a property, and the property is a control. The control has a property, is a motor handler. Maybe someone should say, should ask that why we are not giving a direct property of a motor handler to the sensor listener. I could answer the question as following. We can have a direct access to the motor handler when we are storing the motor handler as a property in the sensor listener. But I want to filter out some of the functionalities or some of the methods which are inside the motor handler. So what I'm doing is that I'm defining a new class, and in this class I'm storing this instance, and this instance inside the control I can filter out those methods that I want the user be able to use inside the listener. So the old functionalities inside the motor handler wouldn't be visible to the sensor listener, thus I'm filtering out them inside the control class. So I'm hiding some functionalities which are not relevant and they have no use inside the sensor listeners by putting the motor handler as a property inside the control and implementing the corresponding methods to filter out those functionalities. So basically, in a big picture, this is our model for the robot. And let's take a look at the implementation. So as you see, we have different packages, and each package holds different classes. So the control class has a motor handler property, and we are filtering out some, let's say, functionalities that we want to be accessible for the user, which is implementing the listener, and it's using the control. As you see at the very beginning, we have defined an interface iMotor, and the big motor implements the iMotor. If you remember, when we were implementing the test case, I told you that using the interface makes our code more flexible because we can define different motors, and those different motors can be passed to our test class no matter what kind of motor we are using. And we can also mock the motor interface as a mock motor, as you see here, and this mock motor imitates the behavior of the real motors. So we can use this mock information inside our test class. And also there is a robot class which we talked about. It has two property, and this property is a map of the sensors and motors. And why we are using the map? It's more efficient to store the sensors inside the map with a key, so we can access the sensors simply by using the name of the sensor, and we don't need to iterate over the whole list of the sensors to get the sensor that we are looking for. So this is a technique that I'm using here to make the code a little bit more efficient. As we talked earlier about the listener interface, we have a listener interface here, and the listener interface provide us with the number of methods that should be implemented inside each sensor listener. And we have an abstract representation of this interface, which implements the standard methods, which should be consistent between the all in the implementation for the sensor listeners. And we have the actual implementation of the listener, for instance, touch sensor listener, which extends the sensor listener abstract class. And in this implementation, we implement the exact behavior that we are expecting from the touch sensor listeners in the corresponding method. For instance, on sensor sampling has a different behavior in the touch sensor listener as in the ultrasonic. And also we have an event interface and the abstract implementation of the event. And also we have a corresponding implementation based on our need, which extend the event class. So let's take a look at the difference between these two events. A motor event has a direction, but the sensor event don't need to have a direction. So we are adding an extra property to our class, which is a direction. And whenever we are working with the motor event, we can access the motor event implementation and methods through a typecast. So or static type for the motor event is event, but our dynamic is dependent on the initialization, what type of motor that we are initializing in the object we are defining. We have this dynamic type. So let us take a look at the code. And for instance, in the ultrasonic listener, we are initializing a new instance of the motor event. Here at the left side, we have a static type. On the right side, we have a dynamic type. So let's see what happens if I write event here. We'll import the event class from my packet. As you see, we have some problems. What is the problem here? The event is the abstract implementation of the iEvent interface. As you see, inside the event, we don't have the method set direction. So to be able to access this method, my dynamic type should be visible to the compiler. So the solution is to doing a typecast. Let's see what happens if I do a typecast here. As you see, as soon as I'm doing a typecast, my static type, which was event, will be casted to the dynamic type motor event. So I'm accessing to the dynamic type through a typecast, and then I can access the methods which are implemented inside this dynamic part. So let's go back to the implementation. So this is the simply how we can benefit from the differentiating between the static type and dynamic type. And the usage is basically when we are handling this information inside motor handler. So I'm implementing a method called update motor, and in the update motor I'm passing an event. So I don't need to implement two update motor method. And then, for instance, whenever I want to pass a motor event, so whenever I want to pass a motor event, if I don't use this functionalities and using this type of implementation and defining an abstract class and then using a static type to reference the type that is coming inside the method. So if we ignore this way that we that we just discussed, I mean, if we ignore this, then just only define a class motor event and then class sensor event, I need to implement for the same type of job different methods multiple times to just only be able to pass a different signatures to my method. So by using the polymorphism, I'm trying to reuse my code for different purposes. So the reusability is increasing by implementing and extending a class from the interface and from the abstract class. So as you see, I'm just implementing the update motor method once with the signature which refer to the event, and whenever a motor event or sensor event coming through, this signatures is perfectly fine because it allows me to pass the event to my inside the method and process that event inside the method. So here I can decide what to do with the method based on the type that it has. So as you see, I have a if condition here, which take a look at the instance type. So basically, this is nothing more than a typecast, which is implicitly happens and compiler take care of this typecast. So it checks the type of this event, dynamic type of this event, and tells if the dynamic type of this event is a sensor event, do this, If the dynamic type of this event coming through is a motor event, do this. So basically, I'm deciding what to do on a dynamic type after accepting the event. And remember that you cannot instantiate the abstract classes or interfaces. So definitely what's coming here is an extended version of the event. So I can ask for the dynamic type with this simple piece of code. And as you see, we can then process the code and see what to do and decide what to do based on the what type of the motor event is coming and what kind of information, for instance, the direction it contains. So you see the typecast I'm using here. This typecast is necessary because what is coming inside has a static type of event. I don't have this method inside this static type. So I'm doing a typecast because I know the dynamical type is the motor event. So I'm doing a typecast to access those methods which are implemented inside the motor event class. This is all for this video. Thanks for watching. Please do not forget to share and also subscribe to my YouTube channel. And I would be happy if you give me a feedback, comments, or if you have any question, please don't hesitate to ask. And I hope you enjoyed this video.